Okay, so I give back your quizzes. I posted the key. So take a look at it if you have any questions. Let me know. A lot of you had trouble with the second question, which is not unusual, but especially the third question, calculating the equivalent resistance. Remember, all of that material will be applicable to the next exam, which is for your group will be in 2 weeks. So that'll be coming up. I'll post an old exam, probably sometime later this week, to give you an idea of what to expect. Let's see, your group takes it on Friday, right? The Friday lab. So it'll be 2 weeks from this coming Friday. So that'll be the 18th, I think. Okay. All right. Let's see. Any questions? Oh yeah, sorry.
On this Wednesday, we're still not having class. That way we can have.
Yeah, I posted an announcement. So for your class, class is canceled. Yeah. But of course, we'll have the lab on Friday. Okay. Let's see. We're talking about the Biot-Savart law. So we saw that if you have a current carrying wire, we have this form. The one example we did was a segment of wire, and then we looked at the magnetic field somewhere along the perpendicular bisector. And then we saw that if you're far enough up, or if you're close enough to the wire so that you can't see the ends, you end up with just this equation. Of course, the directional comes from the right-hand rule, but then the magnitude just works out to be this. Okay, so this would be for a long, straight wire. And the word long meaning that we can't see the ends. So we we use this for the that example. And we said, well, what if we're close enough to the wire that we can't see the ends? Then we end up with this simple relationship. Okay, and then we said, what happens if you don't have a current, a stream of charge? What if you just have a single charge, like a proton or an electron? And we saw that we could rewrite it this way, because the current is really just Q over time. The Q doesn't change, but if I take dl over time, that's essentially the same thing as the velocity. And so instead of dl cross r hat, we have v cross r hat using the right-hand rule. So let's take a look at, this is number 3 in your homework. So here you have an electron, so it's not a current, it's just a single charge, and it's moving at 15% the speed of light. So that's pretty fast. And there's 4 points labeled A, B, C, and D, and they're all 2 microns from the electron. And so what they want us to find is the magnetic field produced by the electron at each of those 4 points. Okay. So we'll use this relationship. So there's your electron, there's V, and they give us some points here. A and B, D is down here, and C is over here. So they're all equidistant from the electron, and that distance is what's called R, is 2 microns. And then the velocity is 15% the speed of light. So what's the speed of light? 3 times 10 to the 8 meters per second. So yeah, that'll be 4.5 times 10 to the 7 meters per second. Okay. Excuse me, and they also give us some angles there. It looks like there's 2 60-degree angles here and here. Okay. What do we know about the magnetic field at point D? Let's do that one first. That's the easy one. Remember, how do we interpret this? The velocity vector is pointing up along the board. What's the direction of r hat for this point? It points from here to here, right? So what's the angle between V and r hat? 180, so sine of 180 is 0. So the magnetic field at point D, which is 0. Okay, so that's probably far down on the list. Let's take a look. Find the magnetic field of find the magnitude of the magnetic field at point D. So that's got to be 0. Okay, so they agree. Now what about point A? Okay, so here's the charge, r hat points this way. So what's the direction of the magnetic field at point A? V and r hat are in the plane of the board, so it's either into or out of. And remember, it's electrons, so the charge is negative. So V wrapped into r hat points into the board, but then the negative charge points it out. So we know this is out of the board. So then what's the magnitude? So that'll be what? Mu 0 over 4 pi, we have Q, which is just E. We don't have to worry about the minus sign, that's already been taken care of. And then how am I gonna write this out? The r squared down here I'll leave alone. We have the numerical value for that, but then how am I gonna write this out? This will be V, which we know. R hat has a magnitude of 1, and then what do I have to multiply that by because it's a cross product? Yeah, the sine, and what's the angle between those two? 30 degrees, right here. Okay, so sine of 30. Okay. Let's work all of that out. We know the value for mu 0, the 4 pi's will cancel, so it's just 1 times 10 to the minus 7. We have V, they gave that to us. And then what's R? 2 microns in the square. So it's like 9.01. Times 10 to the minus 8 Tesla. Yeah. All right, so let's try it. Okay, so they agree, and then the direction we said was what? Out of the board? So out of the paper? Okay, so they agree. What about a point B down here? What's the angle between V and R hat here? 150, right? So instead of sine of 30, we have the sine of 150. Are they the same? Yeah. So is the magnitude going to be the same? Yeah. So for point B, it'll be the same value. Because all of these stay the same. You just have sine of 150 instead of sine of 30, but it's still a half. Because sine in the second quadrant is also positive. What about the direction? So V, R hat, that's into the board, but then the negative charge flips it. So at these 2 points, what do we know about the field? Same magnitude, same direction. Okay. All right, so let's see if they agree. They do. And it's also out of paper. Okay. Where we got the field at D, that's 0. What about the field at C? Right here. What's the direction? Is it still out of the board?
Mm-hmm.
Yeah, it's still out of the board. What's going to change? Yeah, because instead of sine of 30, we're going to have sine of 90. All right, sine of 30 is a half, sine of 90 is 1. So what do? Just double that? Right? So at point C, still out of the board. Okay. So I'll just write that as 1 times 10 to the minus 7. Let's just make it 1.8. Okay, and it's still out of the paper. And for this one, for D, it was 0. Okay. All right, any questions on that? Now, if an electron is moving this way, what would be the direction of the current that we would describe that motion? That would be down, right? So if the current's flowing down this way, what does the right-hand rule tell us? We saw an alternate way is to take your thumb and point it along the current, and then your fingers wrap around in the direction, right? Well, over here, my fingers are pointing out. Over here, my fingers are pointing in. So it matches. So you could either use that method or just go back to this that you're more used to. Okay. Any questions on this? What would happen if it was a proton? Would anything change?
The direction.
The direction of the field would change. What about the magnitudes? No, because the charge is the same, the speed is the same, the distances are the same, but because it's a positive charge, it would just be different directions. Okay. All right, good. Let's see, and we did this problem. I think we finished it. Yeah, we had to find the X, Y, and Z components. What about this? So you have, instead of one wire, you have 2 wires. They're a few centimeters apart, and they carry currents in opposite directions as shown. And then there's an empty point that they label P, and we want to find the magnetic field there. Let's see, the wires are 4.2 centimeters apart. Okay, let's put it over here. Numbers, it's 12. There's our point P. And let's see, this current is what? Call the side 1, this is 12 amps. Call the side 2, what is that, 24? Okay, what they want is the magnetic field of point P, not due to the entire length of the wire, but just due to those 2 little segments. So right here, and right here. So the DL quantity is what, 1.5 millimeters? R is what, 8 centimeters? Okay, so we have those. So let's see, now the current's flowing this way. See, that's DL for this one, but DL for this one is in this direction.
So I have a question about this.
Yes.
Now, because we have the bottom wire is going to the left, that's.
The current's flowing to the left, yeah.
So that'll give a magnetic push into the board, right?
Yes.
And then the one on the top is also into the board.
Yes.
But then we know as well that the I is twice as much on the bottom.
Yeah.
So, and then they have the same angle, right?
Well, you tell me, are theta and phi the same angle? They're not the same angle, but what about their sign?
Their sign will be this, because it's 8 centimeters away on both sides, right?
Yeah, so there's some symmetry there. So let's find the angles. So this is half the distance, so what's that, 0.021? This is a right angle, and this is what, 0.08? And for the top one, this is theta, so what trig function could I use to find theta? Sine, cosine, or tangent?
Sine.
Sine, yeah. So theta would just be what, the inverse sine of what over what? It's gotta be what? 21 over 80? And why didn't I put the decimal point in there? It's a ratio, yeah, so 21 over 80 is the same as 0.021 over 0.8. So let's see what that gives us. That's gonna be roughly a quarter, so relatively small angle. So the inverse sine is 15.2 degrees. So what about phi? Not 90. Yeah, because of the symmetry, this is theta right here. So phi is just 180 minus that. So what's 180 minus 15? 165? So what's that, 164.8? Are the signs of those two the same? It's S-I-N sign.
Yeah.
Yeah, just do this. But if this is theta, this is phi, yeah, the signs are the same. Okay, and this current is twice that, so what's your argument?
So my argument is that we can just treat it as one wire that has 36 amps.
Okay, you could probably do that. Because of the symmetry, and the 36 amps would be flowing through the,
Right there. Because they're the same direction, right?
yeah, you could do the same.
Right.
Yeah, you could do that.
Okay.
We're not going to, but you could.
Okay.
Yeah.
It would be a shortcut.
Yeah, because of the symmetry, because these are basically opposite each other and the angles give you the same sign.
Mm-hmm.
Okay. All right, so let's work this out.
But not just 12. It's not really cast each other out. They're pushing different directions.
Yeah, so let's see, what is the direction?
Into the board.
So B1 and B2 are both into the board.
Oh, they're both in. I see.
Right.
I see what
DL cross R hat's in. DL cross R hat is also in. We've got the two angles, so yeah, what would the B field be? We have what, DL? R hat has unit vector one, or unit length 1, this is sine theta. And R squared, this one would just be what? Yeah, so they should be the same exact value.
Okay.
So let's see what we get. So 4 pi's cancel when we put in the value for mu. And what's I1? 12. And DL is 1.5 millimeters. And 15.2. Yeah, so they're both 7.37 times 10 to the minus 8 Tesla.
Except one of them is double that, right? 'Cause it's-
Yeah, wait, what about the eye?
Oh yeah, so yeah, if we just double it, sorry. So 1.47 times 10 to the minus 7. Okay. So then the total is what? Since they're both in, they're parallel to each other, so we just add them up. So So it works at, the total works out to be 2.21 times 10 to the minus 7, okay. So let's get the direction first. 33. You know, whether they were hoping you would see that, I don't know, but it's good that you did. So our unit is what, the Tesla? Okay. Let's see if they agree. And they do. Okay. Any questions on this? Any questions on the angle or the direction? Yeah?
What is the value for the?
So in SI, the value for mu is this. The way it's usually written is this. But in Biot-Savart law, the 4 pi cancels, so you can just use it as 1 times 10 to the minus 7. In any other situation, like the special case for the magnetic field due to long straight wire, you can't do that. Because the 4 pi in the bottom actually becomes a 2 pi. So it's 2 times 10 to the minus 7. Yeah, so just be careful of that. Your book most likely writes it this way, that's the way most books do. Probably to remind you that it's similar or analogous to epsilon 0, the permittivity. Any other questions on this, on the direction or the magnitude? Okay, I think that was all they wanted. All right, what about this? So again, if you want to create a magnetic field, you could just use a long straight wire, but it turns out that's not very efficient. To get an appreciable field, you have to send a lot of current through it. So a better way is to use a loop. So let's look at the B field due to a current loop. So maybe something like this. We won't worry about the power supply, we'll have some current flowing around. We'll situate the loop like this. The x-axis will be perpendicular to the plane of the loop, and so maybe we're standing out here, we want to know what the magnetic field is. Okay, so again, we just have to be careful with our drawing. Let's call this x, we'll call this y, and we'll call this z. And the loop will be oriented like this, so it'll be in the YZ plane. And the current will just be like this. So the current is flowing this way. Right here. So this portion of the loop is closer to you than this portion back here. And of course, the center of the loop will be right at the origin. And we'll give the loop a radius, we'll call it little a. Okay. And I'm standing out here. And there's a point P right here, and I want to know what the magnetic field is there. Okay. So again, what do I do? To use the Biot-Savart law, we need this. So let's work on the direction first. Okay. So let's say we can choose any number, any portion on here to be DL because there's an infinite number of them. Let's pick the portion right up here. So DL is pointing right out of the board at you. In this drawing, it's pointing like this. It's parallel to the z-axis. Okay. So that's DL. My thumb is R hat. Now, R hat has to point down like that, right, towards point P. What's the angle between DL and R hat? What is it? What'd you say?
90?
It's 90 degrees, right? So for our cross product, we have sine of 90, which is just 1. Now what happens as I work my way around here? Well, my finger will be DL, my thumb will be R hat. No matter where I'm at on this, I don't know if you can see that, but as I work my way around, the angle between DL and R hat will always be 90 degrees. So that greatly simplifies the cross product. In my drawing here, I'll do this. This is R, which we can get from a right triangle. That's not a problem. This angle right here is 90 degrees. Okay. So DL times 1 times sine of 90. The current is the same for every single segment, so I can pull that outside. I just need to know what R is. But what does the cross product give me? So the fingers of my right hand are DL. Now R hat's pointing down this way, so I have to wrap it this way, so my thumb points like this. Now that's the contribution due to a single DL, so that means this is just dB. Because of a cross product, that's a right angle right there. What's going to happen as I work my way around? So I start up here and I work my way around, and I look at how dB changes. What's dB going to do? Let's say this is dB. What's going to happen as I work my way around? dB is basically going to do this. It's going to trace out the surface of a cone, right? So what will happen to the y components of dB? So the dB that I drew is right here, right? If this traces out the surface of a cone, what happens to the y component? Not
Cancel.
there.
They cancel.
They cancel, right? What about the z component?
Same thing.
Cancel, right? So the only component that's left is this component right here. So by and bz are both 0 by symmetry. Because I deliberately chose the origins to be at the very center of the loop. And I put the loop in the plane defined by 2 axes. So what do I need is this. I need that angle, right? So what's dBx? Because that's the only component that's going to survive. So that'll be dB times what? In that drawing.
L.
No, I just want the x component of dB. So I take the magnitude of dB, what do I multiply it by? Cosine of theta. Okay. Okay, now all I need is theta and r. Let's go back here. Okay. So here's a right triangle. This is x, that's not going to vary. This is the radius of the loop. This is r. So what's r equal to?
Square root of a squared plus x squared.
Yeah, it's just a squared plus x squared. Square root. Is r a constant for every little dl in that loop? Yeah. Can we factor it out of the integral? Yeah. Now we have to worry about that cosine of theta. That's a right angle. I define this as theta. Is theta inside this right triangle that I originally drew?
Yeah.
Yeah, because if I call this phi, if this is 90, then phi plus theta is 90 degrees. So where is theta inside that right triangle? Yeah, it's right up here. Now I need the cosine of theta, so in that right triangle I just drew, what's cosine of theta?
X.
A over R. Are A and R constant? Yeah. So it looks like I can factor out a lot of things. Alright, so let's write down the Biot-Savart law. Factor out what's constant, and then do the integral. Factor out the I. There's my integral. I have dl times 1 times the sine of 90 degrees. That takes care of my cross product, r squared. And then I have to multiply it by cosine of theta. This is 1, that's 1. Factor out the r squared. Factor out the cosine of theta. And I'm just left with that. The simplest integral you can get. If I integrate dl, I just get the length of the loop. What's the length of the loop? Just the circumference. So there's the 2 pi a. I have the a from before, then I have r cubed. Okay. So it looks like we just get this.
What happens with 4 pi?
That's right there. See if you were paying attention. Okay, so let's see. So the pi's canceled, one of the 2's canceled. So it looks like we have. So I'm left with what? 2 downstairs, and then r is just this. So that's our B field at that point B. Okay. Any questions on how I got that? So what happens when x is 0? What's my B field become?
0?
No.
No, maximum.
I'm standing right here, dead center. So what's B? What happens to the x is 0? That drops out. What happens to the a? You're left with just an
They
a in the
cancel.
denominator. So you get a nice, simple result.
Mu I over 2.
That's it. And the direction, tell me the direction. I'm standing right there.
Just in the x direction.
Right, so it's perpendicular to the plane of the loop. Okay.
And quick question.
Yeah.
That, the bx at the bottom, mu 0 I a squared?
Yeah. Because there's 2 a's here.
Mm-hmm.
This a comes from the cosine.
Mm-hmm.
This is the circumference.
Okay.
A times a.
And then, if x is 0, do those 2 a squareds both cancel each other?
No, then you have, in the denominator, you have a squared to the 3/2 power, which is a cubed.
Oh, got it. Thank you.
And so 2 of them cancel, so you're left with just 1.
Okay.
If you put in the units for everything, you'll get Tesla.
Okay.
Okay. It looks almost like the equation that we have for the magnetic field due to a long straight wire, right? The only thing it's missing is pi.
Right.
Okay. So this is a much better way to do it, because what happens if you make this loop relatively small in radius and you're able to send a large current through it? Right here, you're gonna get a relatively strong field. even better, what happens if I take a long piece of wire, maybe 2 meters long, and I do this? And I just keep wrapping it, turn after turn after turn, maybe 1,000 turns.
Solenoid.
Yeah, you form a solenoid, you get a nice, strong, very strong magnetic field along the axis of that coil. So that's generally the way you produce very strong, uniform magnetic fields. So we'll see this thing called a solenoid is analogous to a parallel plate capacitor, but you're producing a magnetic field instead of an electric. All right, let's take a look at, let's try this one. So here you have a closely wound circular coil. Its radius is 2.3 centimeters, so its radius is about 1 inch, but it has 730 turns. What must be the current in the coil if the magnetic field at the center of the coil is 0.079 Tesla? Okay, so they're giving us the value of the field. We want to figure out what the current will be, right? Yeah. So I'll take our result. Now we have n number of turns, so each turn will produce that field, so I just multiply it by n. And they tell us n is what, 730? A is what? 2.3 centimeters, and the B field you want to create is 0.079 Tesla. Okay, so for part A, we just want to know what the current is. Okay. All right, so we have everything, so let's just multiply that out.
Sorry, can you remind me what, the constant mu is?
Yeah.
Before?
So again, mu0 is this. Now, if you work out the 4 pi, it works out to be 1.2, I think it's 1.257. It's 1.257 times 10 to the minus 6 decimeters per Kelvin. So it's just a constant.
Thanks, I think I'm right now, so. That was.
All right, so let's just work that out. So u times what, 730, convert that. And what's the B field, 0.079. So you get 3.96 amps. Okay, that's a reasonable current. And this is what? This is about 10 to the minus 2 Tesla, so it's more than 1,000 times stronger than Earth's magnetic field. So it's a substantial field. So by just using a coil, a relatively modest current will produce a nice strong field. So it's relatively straightforward. Okay, let's see if they agree. 3.96 amps. Okay, they agree. Now they say at what distance from the center of the coil, on the axis of the coil, is the magnetic field half the value of the center? So now we got to go back to this form right here. Because we're walking along the axis of the coil, but we're outside the plane of the loops. So for part B, there's the coil, here's the x-axis, we're somewhere out here. And this field is 1/2 of what was it originally, 0.079?
There's a question about that.
Yeah.
If it's half the original, does that mean we just have to find the point where sine of theta is half of the previous one? So it would be sine equals 1, sine of theta equals a half?
What's theta in this case?
The angle between the.
In other words, does theta show up in this equation? That magnetic field that we derive just depends on the current, the radius of the coil, and how far away you are from the plane of the
It,
coil.
it implicitly shows up in X though, right?
Well, there could be, but it's not explicitly in there, so we don't have to worry about an angle.
Okay, fair enough.
Yeah. So let's take this. So we have mu 0 I, a squared, over 2. So we're looking for x. X is our unknown. How far away do we have to be from the coil to get half the strength of the field? Okay. So this, whatever this is, will be 1/2 of what we get using this. So that's mu 0 I n over 2a. Okay. Do I get any cancellations? Looks like a 2 cancels, the mu 0, the I cancels, and I can combine the a to see what we get. So let's see, the mu 0 I goes out, so I'm left with what? Looks like 2a cubed. So if I bring this up here, this 2 cancels.
And were we meant to have n on both sides as well?
Yeah.
Yeah, sorry, there should be an n over here. Yeah, so the mu 0 I n all cancel, so I'm left with 2a cubed. And actually, let's do this. So the mu 0 I n cancels, the 2 cancels here, I bring this up here, this is a 1. Let's bring this up. So I just get this. What's that squared? 3/2. Okay. Can I cancel anything else? Can't cancel anything else. So let's get rid of the exponent there. So let's multiply both sides, or raise both sides to the 2/3 power. Get that. So 2 to the 2/3. What's a cubed to the 2/3?
A squared.
A squared. Let's bring this over. I can factor out an a squared. So I have 2 to the 2/3 minus 1. Then if I take the square root of both sides, I get x. This becomes a. This is just okay. So I have everything on the right-hand side, so let's work it out. So 2 squared is what? 4, so I want the cube root of 4. I'll subtract 1 from that, then take the square root of the whole thing, and then multiply by a, which was what, 0.023? So it looks like 1.76 centimeters. So imagine there's a whole bunch of loops right here. Here's the center. I'm literally right here, just a very small distance away. So what does that tell you about the strength of the field? Once you get outside the volume that's enclosed, the magnetic field drops off rapidly. Okay? And that's typical of things like solenoids. Outside, you can assume the magnetic field is basically 0. It's strictly confined inside. Kind of similar to the parallel plate capacitor. The electric field is confined inside. It's generally 0 outside. All right, let's just say grade. I'll put it in meters. I don't know if they want centimeters. So we'll make that meters and see if they agree. And it looks like they do. Okay. All right, any questions on this? Back here, let's try. Actually, let's talk about magnetic flux. You know, several weeks ago we looked at electric flux. We defined what it was and we solved it. What makes it important is that you can use it as an intermediate step to form Gauss's law. And then what was important about Gauss's law, you could use it to calculate the electric field due to different charge distributions. So it shouldn't surprise you that there is a quantity called magnetic flux. Okay. So instead of phi sub E, we'll call it phi sub B. How did we define electric flux? What was it? It's a measure of what? The number of electric field lines that pass through some surface area or some cross-sectional area. Magnetic flux will have the exact same definition. So it's a measure of how well a B field penetrates or passes through an area. It could be a cross-sectional area or a surface area if it includes some volume. So what do you think how are we going to define it? How did we define electric flux? First of all, was electric flux a scalar or a vector? The scalar, right? And it depends on two vectors, the electric field and the area. So what type of product must it be? A dot product. Same thing here. It'll depend on the magnetic field vector and an area vector, but this thing's a scalar, so it's got to be a dot product. So there you go. Okay, we saw how to convert an area into a vector. If it's a cross-sectional area, you're generally free to choose the direction of it. But what if the area encloses a volume? Then it always points how? Outward. Yeah, that's the convention. Okay, same thing here. So there's nothing new. The only thing that's different is the unit. Remember, for electric flux, there was no special unit. It was just Newton meter squared per coulomb. This has its own unit. So what do we have here? We have Tesla meters squared. So this is what's called a Weber or a Weber, depending on how you pronounce it. Weber was a German scientist who worked with Gauss on electromagnetism. So when we abbreviate it, it would be capital W, but we also have to add another letter because what would that confuse us with? Watts, yeah, so we have to put a little V in there. Okay. All right, so that's the only difference. There is a special unit for it, but it's just a Tesla meter squared. All right. Oh, what else? Once we defined electric flux about a month ago, we saw how else could you write it? With Gauss's law. What did it equal? It was the ratio of two scalars, right? It was Q enclosed over some constant. Okay. And so if your area enclosed any charge, there was a flux through it. What if your area, no matter how strange it was, enclosed no charge? The flux was 0, right? Same thing here. If your area encloses some source of the magnetic field, then there's a flux. What's the source of the magnetic field? It's not charge, it's current, moving charges. Yeah, so I think there's a problem that looks like it's very similar to the one you had a few chapters ago with electric flux. See if I can find it real quick. A lot of these are repetitive, so if you're following what I'm doing, you should have no trouble being able to do the rest of them.
There was actually a question from chapter 27. I think that had to do with that.
Was it 27? Maybe it was.
I think we talked about
I thought it was in this chapter. Hang on. Okay, we just did that one.
27 or 26, I think.
This one, correct.
Oh, I have no.
Yeah, it says number 38. It says the figure shows in cross-section several conductors that carry currents through the plane of the figure. So current 1 is flowing into the page, current 2 is flowing out of the page, and current 3 is also flowing out. And they identify the values of the currents in the direction shown. So, okay, so this deals with Ampere's law. So before we do this problem, let's talk about Ampere's law. Just like we saw that once we define this, we didn't really have to worry about it because we just used it as an intermediate step for Gauss's law, and then we use Gauss's law to solve for electric fields. The same thing here. This is, even though we define it, we generally don't worry about it because it's just an intermediate step for a new law called Ampere's law. And so just like the Biot-Savart law was analogous to Coulomb's law, but for magnetic fields, Ampere's law is analogous to Gauss's law. It's another way, and for certain types of current distributions, it greatly simplifies how to calculate the magnetic field. So let's take a look at that. So it's similar to Gauss's law. And what was Gauss's law? That was your steps. Okay. So the question is, could I do the same thing here? Instead of E dot dA, could I take V dot dA and have some similar thing over here? Well, the problem is you can't, because what's one of the things that makes the magnetic field different from the electric field?
Requires movement.
Well, there's always movement involved. There's always 3 dimensions. And what do we know about the structure of the magnetic field lines? They're always closed loops. There's no beginning or end, unlike electric fields. So the problem is that this won't work because there is no beginning or end to any B field. So we can't come up with a similar relationship. So instead of an area integral, what Ampere was able to show is that you use what's called a line integral. The idea is the same, but instead of integrating over an area, you're integrating over a line or a path. So instead of B dot dA, use B dot dL. And then you define what dl is, and then when you integrate, you're integrating over some path, so you have a beginning and an end. Okay, so we have this. So remember, for electric fields, this is our source, and then this is some constant. So what Ampere is saying is that we're going to do something very similar, but instead of an area integral, we'll have a line integral. We have to have the source and we have to have a constant over here. The question is, what's the arrangement? If you just play around with the units, you could probably figure out what it is. What's the source of the magnetic field? That's just current, right? So we're gonna have current, and our magnetic constant is this. So is it just mu 0 times I, or is it some ratio? Well, if you just work out the units, it works out with the units. So this is Ampere's law. And we use it kind of the same way with Gauss's law. It's just instead of an area, you have a line or a path. Okay. Let's take a look at an example. So we talked about the solenoid, which is basically a coil used to create a nice strong field. So let's look at that. This thing has various names. Sometimes we'll call it a coil. Later on, we'll call it an inductor. The book probably keeps using the word solenoid. They're all synonyms. They all mean the same thing. You basically take a long piece of wire and you wrap it around a cylindrical form. You pull that form out, what you're left with is that. It looks like basically a spring. But you're not worried about the mechanics, you're worried about sending current through it. Okay. What you find is that if I blow this up and kind of expand it out, what happens is the magnetic field points like that. Because for each individual loop or each individual turn, we already know that the magnetic field has to be perpendicular to the plane of that turn. And so you're simply adding up a huge number of them because you generally have a large number of turns. So the question is what is the magnetic field? How do we calculate it? Well, we can take that equation that we had before that we derived for the single current loop, but there's actually a better form, and we can get that from Ampere's law. Figure all this. Let's take this and let's take a cross section. So let's imagine we take some scissors and we cut it this way, and I open it up. So I see something like this. So these are each of the turns. And let's say the solenoid has a length, let's call it L. So it's just a certain number of meters or centimeters. Now I'm sending a current in like this. Okay, the other side looks like this. So let's have the current flow is coming out on this side. And then it's going back in on this side. It's really just one piece of wire, so the current is the same everywhere. Okay, so by the right-hand rule, if the current is flowing through each turn this way, the magnetic field will point this way. And as long as you're far away from the end, you can assume the field is uniform. Okay. So think back to Gauss's law. What did we do? We often came up with an imaginary or make-believe surface area, and we tried to pick a surface area that would exploit some symmetry to try to make the integrals or the dot products as simple as possible. Well, here, instead of an area, I have to have a line or a path. Okay, so I've got a nice B field right here. I'm going to be taking the dot product of B with some path. So I want the angle to either be 0, 90, or 180. That'll make the left-hand side there nice and simple. So what I can do is just do this. It's imaginary, so I can make it any shape I want. So I'll just make it rectangular. Okay, so I've got 4 paths there. I'll just label them. Call this path 1. this path 2, this path 3, and this path 4. Now DL has to have a direction. Okay. So let's take DL1 like this. DL2 will be like this. DL4 will be like this. And DL3 out here will be like this. Okay. So I'm just going around in a clockwise fashion. All right. So I can take my overall integral and break it up into 4 parts and just add them together. So this will just be b dot dl1 plus b dot dl2 plus b dot dl3 plus b dot dl4. Okay. But it's not going to be that complicated because we know 2 of them right away drop out, right? What's the angle between the B field and DL2 and DL4? What's the angle between those two paths and the B field?
90.
90. Cosine of 90 from the dot product is 0. So these 2 drop out because of 90 degrees between the 2 vectors that comprise the dot product. This one over here, if I assume that this is far away, right, because it's an imaginary path, so I'm free to do that, then the B field out here basically is 0, so I don't have to worry about it. So if my 4 paths is the only one that I have to worry about. Okay. So I have the integral of b dot dl1. If I start right here and I walk along this path, if I'm far away from the ends of the solenoid, does the magnetic field change its strength or direction? No. So I can factor that outside. What's the angle between DL1 and the B field? Cosine of 0 is just 1. I don't have to worry about that. The integral of DL is just L. So I get just BL. Okay. So we saw that the integral of B dot DL is equal to mu 0 I. Well, we've already worked out this integral. So this is equal to mu 0 I. Okay. Now there's n number of turns, right? So as far as the interior here is concerned, this is mu 0 I times n. So what's the B field? It's just mu 0 I n over L. And that's it. Now we can make that look a little simpler if we define a quantity called little n. And we'll call this is what your book calls the turn density. And all little n is the number of turns divided by the actual physical length of the solenoid. So we get something that looks a little bit nicer. It's just mu 0 little n I. Okay, so that's the equation that we'll use for a large coil, a solenoid, and inductor to figure out the B field. And so if you have a nice large N and you put in a moderate current, and especially if the radius, the cross-sectional area is pretty small, the B field could be quite large. Okay. So let's go back to this problem. So they give us these 3 currents, and they give us these 3 arbitrary, I guess, areas. So what they want to know is what's the line integral for path A? So this path A, now they don't give us any dimensions for it, they don't tell us how wide it is, how long it is, does it contain any sources of the magnetic field? It doesn't. So just like with electric flux, that means the magnetic flux is zero, so that means the B field is zero. Okay. Path B, now path B contains I1, which points in. And it says the integral involves going around the path in the counterclockwise direction. Okay, so if my thumb is pointing in, the fingers of my right hand are going clockwise, which is opposite of what they're saying is positive. So that should be a negative number that we put in there. Okay, so what's this number, 38? Okay, so here's path B. We've got this current going in, we call it I1. What was I1? 3.5 amps? So the integral of B dot DL is equal to this. Okay. Now, according to them, they're taking counterclockwise to be positive. Here, we're going clockwise according to the right-hand rule, so we'll make this negative. I think that's what they want us to do. Let's see. So we have the current, and we just have to multiply by mu zero, which we all know what that is. So I have I'll just round it off, 4.4. Times 10 to the minus 6. And what do I have here? I have Tesla meters. So let's see if that's what they want. Yeah, the integral involves going around the path in a counterclockwise direction. Well, here it didn't matter. Here it does. So let's make this negative. So 4.4 times 10 to the minus 6. Let's see if they agree. And they do. Okay. So what about path C? So C encloses both of these. So we already have the contribution from I1, we just have to add in a positive contribution from I2, because if I2 is pointing out, the fingers of my right hand are counterclockwise, which is positive. So what would that equal? So that would be minus mu 0 I1 plus mu 0, what is that, I2? I2 is 6.1. Okay. So this contribution will dominate this, so we should get a positive number. So 6.1, so I get 3.3 times 10 to the minus 6. So that should be positive. And they agree. So then what do you think you'll do for part D? So it encloses all three currents. The contributions from I2 and I3 will be positive, the one from I1 is negative. Okay, so it's very similar. So even though it's a line integral, you're going to want to think about it the same way that we did the idea of electric flux when we use Gauss's law. Okay, any questions on this? Yeah.
So, I don't really understand why so I don't understand how this is analogous to flux, because when we were doing flux, we take some area, we say, okay, all of the electric field lines that cross through this area, that's what the electric flux is. But I don't really understand why we're taking a path for magnetic flux, or really what magnetic flux
Well,
is.
part of it has to do with the fact that magnetic field lines don't have a beginning and an end,
Mhm.
right? And if you use the right-hand rule, if you see a B field like this, what's important is that the plane defined by the B field is perpendicular to the current.
Yeah.
So the nice thing about Gauss's law and electric charge is it's very visible. You
Yeah.
can make sense of it because it resembles what you're used to from gravity.
Mm.
Magnetism is completely different. And so the simple argument is that you can't use an area integral because you're never going to have B field lines passing through an area. Because no matter how complicated the situation is, the number of B field lines that pass in will equal the number that pass out because they're always form closed loops.
So I understand that if you take an enclosed surface, the B fields coming in and out will always be the same. But I guess I don't understand what the magnetic flux is defined as opposed to,
For our purposes, just assume it's just the same as electric flux. It's simply a measure of how many or how much of a B field passes through some area. And that could be a real area or an arbitrary one.
so it's how many B fields pass through the line that we're calculating? The line that we're using?
No, for flux, you have to, it's an area by definition. The problem is that when you try to do the same thing that we did weeks ago with Gauss's law, it doesn't work. Because the B fields don't have any beginning or end, so you can't use an area integral.
So I think I understand what the B field, what the magnetic flux is not, and why we can't use that approach. I don't understand what it is. You know, like
You mean the magnetic field or the magnetic flux?
the flux.
The simple answer would be, like I said before,
Mm-hmm.
and just leave it at that.
Just don't think about it?
Yeah, because without using vector analysis, it's going to be hard to explain what it is exactly. I often don't talk about it, but your book brings it up, so I mention it.
Okay.
Because you actually don't need it, because all you need is Ampere's law. And at this level, it's not, I don't know if I can give you a definition that would make any more sense than what I just said. You can't use Gauss's law, so you have to come up with another way to integrate the magnetic field over some region of space. If you can't use an area, the only thing that's left is a line, a path. Right?
I'll look it up somewhere else. That's okay.
Think of it this way. Do you understand the Biot-Savart law?
Yeah.
That's all. That's all you need. Remember, Gauss's law is just a modification of Coulomb's law. You don't ever have to use Gauss's law. You can just use Coulomb's law. The problem is it gets really complicated. But in principle, it will always work. The Biot-Savart law will always work. You don't have to worry about Ampere's law.
Okay.
It's just that in a lot of cases, real cases, the Biot-Savart law is just really, really complicated. So if this doesn't make any sense, don't worry too much about it. Just realize that ultimately the Biot-Savart law will always give you the correct answer for the magnitude and the direction.
Okay.
Does that help?
Not really,
Yeah,
but
it is confusing.
well, I think the problem is that I just don't have a mental understanding of what exactly is happening here or what I'm even calculating, and so it makes it difficult for me. But if you're saying, well, what we can do is say, okay, this applies here. You're given this loop, calculate this thing. I understand that I can apply.
Yeah,
this
in some way it's just an algorithm.
Yeah.
So we're simply taking this line integral, and ultimately all we have to do is work this out.
Okay.
And based on the direction they choose positive, we just have to figure out whether it's positive or negative.
Got it.
If you don't understand anything beyond that, that's fine.
Okay.
With a course like this, the authors and us, there's certain things we have to cover. Some of them we can cover very well. others you can't, because without a more advanced understanding, it just doesn't make any sense.
Mm.
And it's kind of unfortunate. But Ampere's law is pretty important. You'll see it in other courses if you're an engineering major, and so we have to cover it.
Okay.
Do we always cover it well? No. Because I don't know if I could explain it in a way that's make it easier to understand beyond what I've already explained.
Okay.
Later on when you take, have you had Calc 3?
No.
When you take Calc 3, you'll run into this. When
Okay.
you talk about what's called the divergence theorem and Stokes theorem,
Yeah.
which are applications of vector analysis.
I'm
You'll
not-
run into situations like this, and it will probably make a little bit more sense.
I am familiar with those, yeah.
But that is not a requirement for this class.
Got it.
So there's only so much depth I can go into.
Later courses will explain this further.
Yeah.
Okay.
Yeah, because all engineers have to take up to Calc 3 and differential equations. And depending on the type of engineering you're in, you'll run into these situations.
Okay, thank you.
Factors.
Yeah, that answers my question.
Yeah, but it's a good point. I mean, if it's a little confusing, that's okay. Read through the chat. This is in chapter 28. Read through that section and see if it makes any more sense. See what examples they do.
Okay.
But if you're still not sure, that's okay.
All right.
Because I can't think of me asking anything deeper than what's in this problem.
Got it. Know this equation.
What's that?
Know this equation, basically.
Right.
Okay.
All right, let's see. I think we answered everything, right? Well, I'll let you do this part because it's just an extension of the first three. So let's see here. So let's talk about. Okay, this is another solenoid problem. What was it? There was something right here. Yeah, let's talk about two wires, because you'll need this in lab. So last week, we did a problem where you had a segment of a wire, current was passing through it, and it interacted with a magnetic field that felt a force. And then you could use that to build a balance, so you could hang some weight, and if you send the current in the correct direction, the magnetic force will balance the gravitational force. You remember that problem? Yeah, we did it last week. I think it's in chapter 27. So the question is, what happens if you have two wires that are parallel and you have currents flowing through them? Is there an interaction between the two wires? Because each wire will produce its own magnetic field, and the current in the other one should interact with it. So let's go back and look at magnetic force. Because it turns out this is important. Let's say we have two wires like this, they're parallel. They're separated by a distance r. And let's say we have two parallel currents. Maybe they're different numbers of amps, but they're flowing in the same direction. Okay, so I'll call this 1 and this one 2. So what is the direction of the magnetic field produced by this current down in this region here? So I take the thumb of my right hand, my fingers wrap around this way, so the magnetic field will come down here. So along the segment where this wire is, I get a magnetic field B1 due to I1 pointing into the board. What's the direction of the magnetic field produced by this current up here in this region?
Out of the board.
That's out of the board. Okay, no problem. That takes care of the Biot-Savart law. But now, I1 will interact with B2, and I2 will interact with B1. So you'll have two magnetic forces. So let's just work out what that is. Okay, so we've got the direction, so let's work out the magnitudes. What's B1 and B2? We're going to assume that the distance here is pretty small, so we're just going to use the simple result that we got from the Biot-Savart law. So this will be what? U0 I1
So we're gonna push away from each other.
over 2 pi r. You know, because this position down here is a distance r away from the source of this magnetic field. This one will be mu 0 I2 over 2 pi r. Okay. Let's call the interaction between this current and V1, let's call that F2 because it's acting on wire 2. First of all, what's the direction of the magnetic force on this wire due to this interaction? Remember, it's what? IL cross B? So the fingers on my right hand point to the right, the B field's pointing in, so it's pointing up. So that'll be F2. Okay. The angles are 90 degrees, so this works out to be I2, L2, B1. What about the direction of F1? Well, that's going to be I1 times L1 cross B2.
But downward.
That'll be down. So these two wires are now attracted to each other. Okay. Again, the angles are 90, so I don't have to worry about cross product anymore. I just get this. Okay. So F1 is just this. B2 is this. F2 would just be this. We're going to let L1 equal L2. So the lengths of the wires will be the same. Those two force equations that I just wrote down, is there any difference in them?
Other than direction?
Other than direction, are their magnitudes the same? Yeah. They're exactly the same. So F1 equals F2, whether the currents are the same or not.
Right.
What if you set I1 equal to I2 and you make R equal to 1 meter? Then what do I get? Well, I can get rid of the subscripts. What happens to the currents? I square them. If I divide through by the length, I get the force per unit length, and it works out to be this. Now, what's our value for mu 0? It's 4 pi times 10 to the minus 7. So this works out to be 2 times 10 to the minus 7 pi squared. Okay. So if you remember, when you first learn, probably in Physics 41, when you learn about the SI system, there's thousands of different physical quantities that you can measure, but there's 7 base quantities that the system is founded on. What are they? What are the 7 basic physical quantities that we use in the international system?
Mass in kilograms.
Yeah, there's the kilogram, the second, what else? The meter,
Yeah.
the mole, Kelvin, something called luminous intensity. It's called a candela, and there's one more, the amp. It's kind of strange, right? Because for, we use mass as a basic unit. Why don't we use charge? Why do we use the flow of charge as a base unit? Well, if you think about it, it's actually quite difficult to isolate charge and keep it isolated, simply because of the way nature works. It's actually hard to isolate and keep isolated a given amount of charge. So trying to use the Coulomb as a base unit is difficult. Using the amp is actually much simpler because of this. What happens if I set this distance to be 1 meter, and I have a power supply over here, and I guarantee that both currents are exactly the same. And if I put a little strain gauge here, so as the wires are attracted to each other, they compress the strain gauge. Then that strain gauge gives me a force per unit length of 2 times 10 minus 7 newtons per meter. That tells me what's the exact value of the currents flowing through those two wires.
That's the definition of an ampere?
Yeah, it's exactly 1 amp. So back in the 19th century, scientists realized that this was a convenient way to form a base unit. So that's why the coulomb is not a base unit, the flow of charge, the current is, because it's very easy to duplicate this in a laboratory. Okay, so that's why, like I said, this week in lab, when you do the magnetic balance experiment, what you're gonna do is something slightly different. Instead of having the currents flow in the same direction, they'll flow in opposite directions. So then the forces will be opposite to each other. So if you'll have a movable bar, when you bring it to equilibrium, you'll locate its position. If you put a tiny mass on top of it, the bar gets deflected down. If you send current through a stationary bar and the movable bar in opposite directions, the magnetic force will bring it back to equilibrium. You'll take a set of data, and then from that data, you'll plot it. You will calculate a numerical value for this and see how close you get. And if you do it correctly, you'll get pretty darn close. Okay. About 6 years ago, this was all cast aside. The units are no longer based on some experiment that you do. They're all based on the known physical constants of the universe. But up until fairly recently, this is the way the National Laboratory would define what a coulomb is so that everybody could calibrate their meters correctly. Not a coulomb, an amp. Okay, and then you'll use something like this in lab this week.
What happened 6 years ago?
They wanted to, the people that govern this, the International Union, if you're in applied chemistry, but one of the groups is a units group. The problem was the kilogram. How were units, 100 years ago, if I started my own country and nobody invaded me and I was able to keep my own country, and I wanted to standardize weights and measures so I could trade with the rest of the world, what would I have to do? How would I know what a meter is, a kilogram is, and so forth? I'd have to go to Paris and get a copy of the official weights.
Yeah.
And so there used to be, or there still is, a platinum iridium cylinder that is the kilogram. And then the idea is that you make an exact duplicate of it, you compare it, then you take it back to your country, then you can make as many duplicates as you want. The problem is that you're basing your unit on a physical artifact. And so you've got to make sure, first of all, nobody steals it. And you got to make sure you keep it so it doesn't corrode, it doesn't gain mass or lose mass. You have to keep it under very special conditions. What scientists found is that for some reason, all of the kilogram masses that they had stored were slightly gaining mass. And they couldn't figure out why. It had
Gaining mass?
Had nothing to do with oxidation or anything, or any type of corrosion. They could not figure it out. And so for years, they had been trying to come up with a way to get rid of the kilogram. That was the one thing they could not get rid of. And they finally figured out a way to do it about 10 years ago. They use what's called a watt balance. And what it does is it allows you to make electrical measurements and convert those into a mass. And so all of that stuff that was stored in the vaults of Paris, it's still there, but nobody uses it. It's all based on physical constants. Yeah, if you look it up, just look up SI system new definitions. It came out about 8 years ago, 6 years ago.
Okay.
Right before COVID.
Okay.
And once they got rid of the kilogram, then they knew they could get rid of those. And so now everything is based on the speed of light, the gravitational constant, what else? Epsilon 0, mu 0.
That's nice and clean.
Well, the problem is, so the obvious question is, what happens if I develop a new experiment and I find out that the value for epsilon 0 is wrong?
Then you go insane.
No. What you do is you say the accepted value is correct. You just use the difference to modify every other experiment on Earth. So the speed of light is now a fixed quantity, it will never change. No matter how good we are at measuring the speed of light, the accepted value is fixed for all time. All that will happen is you'll recalibrate your experiments. The beauty of that is that you no longer have to have these experimental artifacts to worry about. Because we know we're able to measure these constants at such high accuracy and be able to duplicate them. They realize that you don't need these artifacts anymore. Because with the kilogram, if somebody stole it, you're in trouble.
Everyone in the world wouldn't know what to do.
Well, there would be ways around it, but it could be a big problem.
For precision, yeah.
And there used to be a meter, an official meter. It's still there, but it's no longer used because the meter was redefined in terms of the speed of light about 60 years ago.
Okay.
And so is the second and the other base units.
And the meter was originally like something about the circumference of the Earth.
The meter was originally 1/1,000,000th of the distance from the North Pole to Paris along the longitude of Paris.
Really?
Yeah, so by surveying, you'd figure out what that length is, you divide it by 1,000,000, it was this long, hey, that's a meter.
Who lived at that place in Paris?
It was, I think, in the Academy of Sciences.
Okay.
I forget the exact history, it's a fascinating story.
Sure.
But at the time, that was the only thing you could do.
Sure.
But the problem is that those things can be hard to reproduce, and as your experiments get more accurate, the values change. And that becomes troublesome because then every 10 years you've got to keep altering the values.
Right.
And so a couple decades ago, everybody got together and said, well, we're never going to do that. But they had to come up with a way to define what the experiment is.
You need to find something immutable.
Yeah.
Yeah.
You're familiar with this. Who here's had chemistry? What temperature scale do you use in chemistry?
Celsius for measuring, but then we use Kelvin for math.
Yeah, why do you use Kelvin? What the heck is a Kelvin?
0 in Kelvin is a total absence of heat energy, right?
Yeah, thermal energy, right? What's wrong with degrees Celsius?
You can have a 0 when there's heat.
Who said that?
excess of heat.
Yeah, because the Celsius scale is based on the specific thermal properties of a specific substance called water, H2O. And you don't want that. You want something more universal. That's where the Kelvin scale comes in because it's not based on the thermal properties of anything. It's based on a universal understanding of thermal energy. You use the Celsius scale, but instead of there being negative numbers, they're all positive, and then 0 is the lowest possible temperature.
Yeah, 'cause you get
But the
0
scale is still the same.
and shit.
Yeah. So you're familiar with that. That's the Kelvin scale is used to get around any changes in the thermal properties of the reference substance that you're using. Because if they change, then you've got a serious problem. Right? Okay. Why don't we stop here? So, let's see, I think for this chapter, we're all done. So what I'll do, now remember there won't be class on Wednesday, but I'll see you on Friday. But I think we're done with this material. So the homework for chapter 28 won't be due until next Tuesday. Now let's see, you had a quiz on Friday. Do you want another quiz this Friday? You do? Okay. Maybe I'll give you a break because we won't meet on Wednesday. And the homework's not due until Tuesday. So let me think about it. Because we will definitely have lab. But I'll let you know about the quiz and I'll post an announcement. Okay. All right, before we adjourn, any last minute questions on anything we talked about? Right hand rule, direction, cross products? Okay. If you came in late, I have your quiz. Otherwise, I will see you on Friday.